Good morning, students. Welcome to today's online session on the course EC404 Advanced Communication Systems. Today, I am going to discuss about cellular concepts. It is from Module 5. So, these are the reference text I have used. Wireless Communication Principles and Practice by Theodore S. Rappaport and Advanced Electronic Communication Systems by Wayne Thompson. So, do you know how the name cell phone comes for your mobile phone or mobile device? Have you ever think about that? Okay, we will see it later. So, in early days, when designing a mobile radio system, the main objective was to achieve a large coverage area by using a single high power transmitting antenna. Okay. But while using this approach, a very good coverage was achieved, but it was impossible to reuse those same frequencies throughout the system. Or any attempts to achieve frequency reuse would result in interference. So, a new technology called cellular technology, which will resolve this problem of spectral conjunction and capacity. So, this cellular technology or cellular concept is introduced by Bell Lab. And in this cellular concept, a large single high power transmitting antenna is replaced by many number of small power or low power transmitting antennas. Okay. So, the early mobile radio system achieved a large coverage area. But in the cellular concept, a large geographical area is divided into small geographical regions, and these regions is known as cells. Okay. So, we are locating in a particular small geographical area which is known as cell when considering this cellular concept. Okay. So, our mobile phone is known as a cellular phone. Then this small geographical areas or cells is allotted with a separate frequency and with a separate antenna. Okay. So, the main objective of a wireless system is to effectively use the allocated spectrum. That means without spectral conjunction and with a good capacity. So, in order to in order to use the available spectrum in an efficient manner, we have to reuse the available spectrum or frequency many times. So, that is why this cellular concept is introduced. So, in the cellular concept, we can reuse the same frequency. So, this picture represents the cellular concept. Here, the cells are represented by hexagonal shape and the letters representing different cells. Okay. So, the neighboring cells have different frequencies and located with different antennas. Okay. Then, in theoretical concept, the shape of this cell is considered as a hexagonal shape. Okay. we will see it later why this hexagonal shape is selected. So this is the cellular system architecture. So it comprises of small area which has a low power antenna installed in the form of a unit called base station. Okay, we already seen the GSM system architecture. In that, base station or base transceiver station BTS, that is located with an antenna. Okay, so a cell is located with a base station or base transceiver station or a antenna or a tower. Okay, so that is the structure of a cell. Okay, so it is a small geographical area which is consisting of a small power antenna. So in this figure, many cells which are located with the antennas, and those cells are connected to BSC, or that base stations are connected to BSC, and different BSCs are connected to MSC, and that MSC is connected to PSTN. So that is we already seen in the GSM architecture. Then there are two different types of cells according to the position of the base station or the low power antenna. The first one is edge excited cells. So in edge excited cells, the antenna is located at edge of this hexagonal shape. And second one is center excited cells. In center excited cells, the antenna is located at the center of the hexagon. In edge excited cells, directional antennas are used, and in center excited cells, omnidirectional antennas are used. Okay. So in both cases or in mobile communication, we are using isotropic antennas. Even if it is omnidirectional or indirectional antennas, it is isotropic. That means they have a they are transmitting the power in a spherical manner. So the isotropic antennas are transmitting power in a spherical manner. Then next term is, so another term is footprint of the cell. The transmission of the base station can be detected only if it is within a threshold value. So this area is called footprint or coverage area of the cell. So I already told the antenna is isotropic type. So it is radiating power in a spherical manner. So the footprint of a base station or a cell should be in a circular shape. Okay, that is represented in the figure. So the radiation is, the power is radiated in a circular manner, and this is different antennas are radiating power in circular manner. So there will be some overlapping, and this circular area is known as the footprint of a cell. Okay. Then we will see detail about what is cellular concept. We already told the main objective of cellular system design is to handle as many calls as possible in a given bandwidth in the most efficient way with reliability and quality of service. In order to achieve this objective, the cellular system employs two crucial features. Those are frequency reuse and cell splitting. Okay, so we will see these two features detailed. So before going to frequency reuse, we will see what is a cluster. So group of cells which are having the disjoint frequency or the non-overlapping frequencies are known as cluster. So group of cells which are having the disjoint frequency or the non-overlapping frequencies are known as cluster. Okay. Here in this figure, the cells which is named from A to G, alphabet A to G, represents a cluster. Then again that alphabets A to G are repeating here. So this is also another cluster. So clusters are repeating in a geographical area. Okay. But in a cluster, many cells are there. So in this cluster, there are 7 cells. These 7 cells having different or disjoint frequencies or non-overlapping frequencies. Then the second cluster also having the same set of frequencies. Okay. So that is the idea of a cluster. So these are clusters with different sizes. Here n is equal to 3, here n equal to 4, n equal to 7 and n is equal to 9. Okay. So here the frequencies allocated with the different frequency bands F1, F2 and F3. 3 different frequencies F1, F2 and F3. Again, these colors represent red, blue and green represents the frequency bands for different frequency bands, and that those frequency bands are again repeating here. Again, this F1 will come here, F2 here and F3 here. So these 3 consist of one cluster, and that cluster will repeat again here like that. Here also like that, F1, F2, F3 and F4 are 4 different frequency bands, and those 4 different frequency bands are repeating. Again, it is repeating. So this is one cluster and this is another cluster. The same way here also. So these are the cluster sizes normally using in different technologies. So GSM, the cluster size n is equal to 3 or 4, and CDMA the cluster size n is equal to 1, and in FM cluster size is n is equal to 7 or 9. Now we will see what is the concept frequency reuse. It is also known as frequency planning. So it is a usage of same frequency carrier in different geographical locations that are distant enough. Okay. So here it represents one cluster which consists of 7 cells A to G, and the same cluster is repeating here also. Okay. So A represents one cell with a particular frequency band, and here also this A represents the same frequency band which is repeating here. Okay. So we can say that the distance between this cell A and this cell A, that is the physical distance between the co-channel cells or where the frequency is repeating. So here in A, one frequency is there, frequency band is allocated there, and in this A also same frequency band is allocated. So this cluster is repeating again here also. This cluster is repeating again here also. Okay. So the same frequency bands are using in this cluster also. So in frequency reuse, we can say the 2 different types of channels are there: adjacent channels and co-channel cells. So in adjacent channels, they lie in the same cluster and use different frequency. So in adjacent channel or adjacent cells, they lie in the same cluster, but they are using disjoint frequencies. In co-channel cells, they lie in different clusters, but using same frequency. Okay, so these 2 are the 2 different types of cells. Now we will see what is frequency reuse in detail. Consider a cellular system which has a total of S duplex channels available for use. Okay. So consider that the available bandwidth or frequency spectrum is divided into S channels, S duplex channels, but that means two-way communication. Duplex means two-way communication. So the available spectrum is divided into S channels. Then if each cell is allocated a group of K channels, okay, for each cell there will be K channels. That K will be less than S. Then these S channels are divided among N cells. This S channels, total number of channels is S. These S channels are divided among N cells. That means the total available channels or the total available spectrum is divided among N cells. That means it is divided among a cluster. Okay. So again that frequencies are repeating in the nearby or another cluster also. So the total available channels or total available frequency is divided among one cluster. Okay. So S channels are divided among N cells. So the total number of available radio channels can be expressed as S equal to K into N. So S is the total number of channels, that S equal to K. K is the number of channels allotted to one cell and N is the total number of cells in a cluster. So cluster is the N cells which collectively use the complete set of available frequencies. So N is the number of cells in a cluster. Then if a cluster is replicated M times within the system, the total number of duplex channels C can be used as a measure of capacity and is given by C is equal to M into K into N, or C is equal to M into S. Okay. So these clusters are repeating M times in a system. So the total number of channels used in that system is a measure of capacity of that system. Okay. So C is equal to M into K into N, or M into S. Then the factor N is called the cluster size, and 1 by N is known as frequency reuse factor of a cellular system. 1 by N is called frequency reuse factor of the cellular system. Okay. Then we already told the shape of the cell is considered as a hexagon, and if we consider it as a hexagon, then the number of cells per cluster N can be written as N is equal to I square plus Ij plus J square. So this N will satisfy this equation I square plus Ij plus J square, where I and J are non-negative integers. I and J are non-negative integer numbers. And to find the nearest co-channel neighbor of a particular cell, we should have to follow the steps given below. So to find the nearest co-channel neighbor of a particular cell. Okay. So this is a set of clusters. Here representing one cell A, and that A is repeating in the another cluster also. Now we are going to find out the nearest co-channel cells of A, or nearest repeating cells of A. So here we are considering that I is equal to 3 and J is equal to 2. I is equal to 3 and J is equal to 2. So the first step to find out the nearest co-channel neighbor is move I cells along any chain of hexagons. Move I cells along any chain of hexagons. And second step is turn 60 degrees counterclockwise and move J cells. Okay, so these are the steps to follow. So we will see it here. So A is the considering cell, and we should have to find out the nearest neighbors or nearest cochannel cells of A. First, we will move I cells or I number of cells in each direction. Here I am moving, here I is equal to 3, and I am moving 3 cells in this direction. Okay. Then next step is turn 60 degree and move J number of cells. So this is the direction following, and I need to turn 60 degree from this direction. So I am turning 60 degree from this direction and then move J cells. Here J is equal to 2, and so I am moving 2 cells. Now I will get A again here. So this is one nearest cochannel or cochannel cell of A. Then the same procedure we'll see here also. Move I cells, I is equal to 3, I cells in this direction. So this is the direction, and turn 60 degree counterclockwise. So we are turning 60 degree in counterclockwise direction. So this is the direction. From here I am turning 60 degree in counterclockwise direction, and again move J is equal to 2 cells in this direction. And this is one again another cochannel neighbor of A. Likewise, we can find out all the cochannel neighbors of this cell A. From this, I can see that this I is equal to 3, J is equal to 2, and N should be equal to 19. And these are the cochannel neighbors which are getting without the signal interference. So the minimum distance to the cochannel neighbor. So by following this equation, we can find out, or we can allocate the same frequency again in a cluster without signal interference. Okay. So this is the frequency reuse concept. So we already told these things. If number of cells in a cluster is n, then the frequency reuse factor is 1 by n. And the distance between cochannel cells is also known as reuse distance. Again, we are reusing that same frequency there also. So it is known as reuse distance. Then the distance between the cochannel cells depends on the size of the cluster. Okay. So this cochannel distance will depend upon the size of the cluster. Then more the number of cells in the cluster, more will be the distance between cochannel cells. If the number of cells in a cluster is more, then the distance between the cochannel cells will be also more. So these are the different cluster sizes. N is equal to 3, N is equal to 9, N is equal to 4, N equal to 7. So here we can see that here F1 is here. The nearest cochannel cell of this F1 is this, and this is the distance. And here F1 is here. This is cochannel distance, and here the cochannel distance is this, and here the cochannel distance is this. So from these figures we can see that when the number of cells in a cluster is more, the cochannel distance will also more. Okay. So now you think small cluster size is beneficial or large cluster size is beneficial. Okay. So we are assuming that all the cells are with the equal size and the hexagonal shape, and then think that small cluster size is beneficial or large cluster size is beneficial. Okay, I think you found an answer. We will see from this figure. If here n is equal to 3, that means the cluster consists of 3 cells. Okay. So cluster means all the available frequency band or frequency spectrum is allocated to that cluster, or all the available channels are allocated to that cluster. That means when the number of cells in a cluster is small, the number of channels per each cell will be more. Okay. That means the number of cells in a cluster is low. The number of channels per cell in that cluster is high. That means the user or subscriber can access many number of channels from that cell. Okay. That means it will have more channel capacity. For example, consider that this total number of available channels are 100. Okay. Then in the case of n is equal to 3, in this particular cell, it will get 100 by 3 channels. Okay. If n is equal to 4, when the cluster size is increasing, or n is equal to 4, here in each cell, it will get 100 by 4 channels. Again, in n is equal to 9, in each cell, it will get 100 by 9 channels. That means when the number of cells in a cluster is increasing, the number of channels per cell is decreasing. That means the number of channels available for each subscriber is reducing. Okay. So, if the number of cells in a cluster is low, then the channel capacity will be high. Okay. Again, we can see that if number of cells in a cluster is small, then the co-channel distance will be less. Is it? So, when the co-channel distance is less, what will happen? The chance for signal interference becomes higher. Okay. That means the signal interference will increase. So, when the number of cells in a cluster is increasing, the interference level will reduce. So, we can say that there will be a trade-off between the capacity and the cluster size. So, when the cluster size is small, capacity would increase, but the interference would be more. Then, when the cluster size is large, capacity will be less, but the interference would also be less. So, when designing a cellular system, we are considering these two factors, channel capacity and also the interference level. Then we are deciding the number of cells per cluster, or we are forming the cluster size. Okay. So, when designing a cellular system, these two factors should have to consider the channel capacity and also the interference level. According to that, we are fixing the cluster size. Okay. Now we will see the shape and size of the cell. We already saw that we are using the hexagonal shape. Then here we are seeing that why we are using that hexagonal shape. Okay. So we already told that the antenna used in the cellular system in both cases, edge cell type and center type cells, we are using the isotropic antennas. So isotropic antennas radiated power in a spherical manner, or we can say it is we can consider the circular shape. Okay. So when we considering this circular shape, so this is the circular shape we are considering. So we have to divide a large geographical area into small geographical areas. Okay. So if we divide in circular shape, what will happen is So we are dividing here. Then some portion is remain without coverage. So gaps result in loss of coverage. Also there will be overlapping. Okay. So if we select the circular shape, there will be gap without coverage, and also there will be overlapping that leads to the interference of the signal. Then what are the shapes possible? So now we can see there are three shapes which are possible to cover all the area. The first one is equilateral triangle, second one is square, and third one is hexagon. So these three shapes can cover all the area without gaps. Okay. Now we will see which shape is more suitable. Okay. We already told that the antenna is an isotropic antenna which will radiate the power in a circular manner or the spherical manner, or we can consider when considering in two-dimensional plane, we can consider it as the circular shape. Now we will see which shape will cover more area. Then that shape is suitable for cell shape. Okay. Now in the first case, equilateral triangle, only 17.77% of area is covered by a circle. So this circle represents the radiated power from the isotropic antenna. So when we are taking the equilateral triangle, only 17.77% of area is covered by the circle. Also, again we are placing the triangle here, then also the interference also will be more. Again, second one is square. In square, if you are selecting square shape, only 63.7% of area is covered. Also here also the interference will be here. If we select the hexagon shape, 83% of area is covered. Okay. When compared to these two shapes, this hexagon shape will cover more area by the antenna. Also, the interference or interfering area is low in hexagonal shape only. Okay, so we are assuming that the geographical area is divided into small cells which is having the shape of a hexagon, which is having the shape of a regular hexagon. That means all the sides are equal. Regular hexagon we are taken. Okay, but this is a theoretical concept only. But in practical case, we are having some deviations from this shape. We are not strictly following this hexagonal shape. We are having some deviations from this hexagonal shape. So this is only a theoretical concept for valuation. Okay. So this is all about the cellular concepts and frequency reuse. Then in the next session, we will see cell splitting strategies and also the handoff strategies. Okay, so we will see in the next section. Thank you, students.